of equations is a set of more than one equation. Here we have 3 examples. Notice you can have any kind of equations in your system. It's a system if it has more than one equation. The solution to any system is the set of all points that make both equations true at the same time. So for example, with our system that consisted of the quadratic and the line, the point 2, 22 is one of the points in the solution set. If you put 2 in for x in the quadratic and you put 2 in for x in the line, you get 22 as the y value for both of those equations. Negative 2 times 4 plus 16 times 2 minus 2 is 22. Negative 2 times 2 is negative 4. Negative 4 plus 26 is 22. So 2 for x, 22 for y is one of the points in the solution set. Another point in that solution set is 7, 12. If you put 7 in for x in the quadratic and 7 in for x in the line, and you do the arithmetic, you get 12 out for y. So the point 7 for x, 12 for y is also in the solution set. And those are the only 2 points in that solution set. Those are the only 2 points that make both of those equations true simultaneously. One of our other examples was a system of 3 linear equations in 3 variables, and the graph of each of those linear equations in 3 variables was a plane. In this case, there's only one point in the whole 3-dimensional space that makes all 3 of those equations true simultaneously. The point negative 2 for x, negative 1 for y, and 4 for z makes all 3 of those equations true. So the point negative 2, negative 1, 4 is the only point in the solution set for that system. In our third example, we have a wave, a quadratic, and a line, and all 3 of these graphs only intersect in the one point, 1 for x, 9 for y. You can find the wave and the parabola intersecting, and you can find the line and the parabola intersecting, and in fact, farther off to the left, cut off by the graph, it looks like the line intersects the wave again, but all 3 of them only intersect in the one point, 1 for x, 9 for y. So the only point in the solution set for this system is that point. A system is inconsistent if there are no solutions to the system. That is, if the solution set is empty. So remember, for a solution to be a solution, it has to make all of the equations true simultaneously. Here we have 3 examples. One example is of 3 linear equations in 3 variables. Thus, we're looking at the graph of 3 planes. All 3 planes do not intersect in the same point. 2 of the planes intersect and 2 of the other planes intersect, but all 3 of them do not intersect at the same point. The next example has some 2-dimensional graphs, a wave, a quadratic, and a line. All 3 of those do not intersect in the same place. Again, the wave intersects the quadratic intersects the line intersects the wave, but all 3 of them do not intersect in the same place. Hence, there is no solution to the system. And then the last example we're already fairly familiar with is parallel lines. We know parallel lines do not intersect because they have the same slope and thus are rising at the same rate. And if they don't start at the same place, they're not going to intersect ever. So that's another example of an inconsistent system. A system is actually linear if all of the variables that are shown in the equation are raised to the first power. No other power. No squares, no cubes, no square roots, no cube roots, no trig functions, no log functions, no exponential functions, just coefficients and variables raised to the first power. I know some people might argue that the definition is if the variables are raised to the first power or 0 power, but anything to the 0 power is 1 except for 0 to the 0 power. And So zero powers just show up as constants anyway. So that's why I'm leaving the definition as linear. If you have a variable, it should be raised to the first power. If that is not the case, then you do not have a linear system. You have a system, it's not a linear system. There are many things that are special about linear systems compared to systems in general. One is that there are three general types of results for solution sets. If the solution set is empty, then the system is inconsistent. There's no solution. Or there might be a single point. All the graphs intersect in a single point. Or you might have infinitely many points, and those infinitely many points lie on some graph, which could be a line or a plane, or it could be all of three-dimensional space or a higher dimension space. You are not going to have just 2 or 3 or 4 distinct solutions. There's either no solution, there's one solution, or there's infinitely many. It's either one or infinitely many, and the infinitely many will lie on some equation. I mean, it could be all of three-dimensional space or four-dimensional space, or it could be a line or a plane. Now, if a system is not linear, then you might have 2 distinct solutions or 3 distinct solutions. But if it's linear, you're either going to have no solution, the system's inconsistent, or there will be one solution, or there will be infinitely many. But nonlinear systems can have some finite number that's not 1. All equations can be solved by graphing. In this case, you can easily read off the grid 222 and 712 are the solutions to this system of a parabola and a line. When the numbers are messier, that's harder to do. You can solve by inspection. By inspection, we mean that you look at the equation and just kind of reason out what numbers plug in work. Again, the cleaner the system, the easier that is to do. Or you can solve by doing algebra using some form of substitution and elimination. I show an example here where both the quadratic equation and the linear equation were solved for y. We're looking for where the y's are the same because you're looking for where the points are the same for both equations. So set the two expressions equal to each other since they're both equal to y. Collect like terms. In this case, it factors nicely because our solutions are 7 and 2. And once we get the solutions for x, to get y, plug both of those values into one of the equations. You should get the same y for both. So I'm choosing to plug them into the line because it's a little bit quicker arithmetic. And we get 712 as one of the solution points and 222 as the second solution point. When your system is linear, there are some methodical tricks that make the substitution and elimination a little bit more streamlined. The more equations you have, the more complicated things are, and then those methodical tricks come in handy. Calculators and software is often programmed with some of these tricks to make it even easier.